WPI's primary tool is OPUS 10, a world-leading logistics optimization program with over 40 years of customer success stories on a wide range of projects. With an easy-to-use graphical user interface, an analyst can quickly develop models and understand the problems being defined. The Explorer allows easy navigation between windows and between models when multiple models are open. The material breakdown structure is a graphical representation of the system and items being defined in the model. Editing is also possible directly from this page. The Support Organization view allows the analyst to quickly understand the support structure of the model being defined. The view also allows a degree of analysis to be carried out. The Data Entry view is where most of the data for the model will be entered. In this example, the view is being filtered for the item that will be processed or updated. Model data is entered through a series of tables, with each table defining a different element of the model. As data is entered, the graphical representations are automatically updated. Data can also be pasted from external sources, such as Excel, or imported via the ODBC interface, directly from external databases. The log pane will show any problems with any aspect of the model and provide status of calculations and results. Note that there are multiple tabs for different types of activity. Once the model is defined, press the Calculate button to execute the model, resulting in the cost-effectiveness curve. A user may also explore the result further using the Analysis view by pressing the Analysis button at the top of the page. The Analysis view allows a deeper understanding of the defined model. As with the Input view, you see the Log pane, Material and Support Organization view, and Explorer window, now with more details and information. We also see a Grid view and Scatter plot. These can be used to check intermediate values like expected actions per year and identify cost drivers. For example, the fan assembly can be seen in relation to all of the items. Back to the Results window, we can see the cost-effectiveness curve. The measures of effectiveness can be readily changed by selecting the desired measure from the drop-down box, as can the combination of systems and stations. From the curve, individual or multiple result points can be selected, and the solutions examined in more detail, either by using the interactive grid view or the report generator. Starting with the grid view, the view allows the analyst to define the parameters to be shown, the result type to be displayed, and various other options, including the ability to sort by entity or sort and filter. In addition, single or multiple points can be selected. Difference between parameters can also be displayed. Tabulated results can be copied and pasted to external tools. The report view allows detailed information and solutions for the model and selected points to be tabulated, printed, copied, or exported. The reports are fully customizable to be adjusted by the analyst. Most of the data in the report is also available to the analyst in the interactive results viewer. SIMLOX is a stochastic discrete event Monte Carlo simulation program. SIMLOX allows detailed analysis of complex systems and organizations, particularly in the air, sea, and land domains, and their interaction with the support organization. Random events during the simulation, such as item failures, allow an assessment of the support organization's ability to handle planned operations. Most SIMLOX models include a user-defined operational profile. Each profile details a series of user-defined missions. Several extensions can be added to the profiles, including deferments, automatic sortie generation, formations, mission-specific failure rates, mission dependencies, random mission generation, and several others. Other user-defined options can also be added, such as resources to carry out maintenance tasks, transfers of systems, items and resources, task breakdowns, damages robbing, lateral resupply transport profiles, time-based changes to the support organization, distributions on time-based activities, and several others. OPUS 10 models can be directly imported into SIMLOX, and for users of OPUS 10, the user interface will be familiar. The Explorer view will allow navigation around the model and between models when multiple models are open. The material breakdown structure is a graphical representation of the systems and items being defined in the model. The support organization view allows the analyst to quickly understand the support structure of the model being defined. The data entry view is where most of the data for the model will be entered. Model data is entered through a series of tables, with each table defining a different element of the model. As data is entered, the graphical representations are automatically updated. Data can also be pasted from external sources, such as Excel, or imported via the ODBC interface directly from external databases. The log pane will show any problems with any aspect of the model and provide status of calculations and results. Note that there are multiple tabs for different activities. The profile view is unique to SIMLOX and allows the analyst to see graphically the time-based operational representations that have been defined, such as resource shift patterns, resupply transport profiles, result collection profiles, and planned operations. Each of these profile views allows detailed information to be checked or understood. For example, the total operating hours requested as a single unit. Once the model is defined, pressing the Calculate button will execute the model. SIMLOX shows a progress window as a summary of each replication through the defined simulation. The number of replications can be explicitly defined or automatically controlled to achieve a desired confidence in the results. Being a discrete event simulation tool allows SIMLOX to represent events in the time dimension. This allows analysis of measures over time, such as system availability, accrued mission time, stock levels, resource availability, and many more. The interactive result window allows the analyst to select the particular area of interest and filter it for specific unit and system combinations. If only overall results are required, this can be selected in the result window. Often the supporting data is needed to complete reports or feed other tools or analysis. SIMLOX has a comprehensive reporting capability that allows all data to be extracted in graphical or tabulated form. All reports, objects, and results can be copied and pasted. Tabulated results can be easily exported to external data repositories. SIMLOX also has a powerful game mode, which allows a single replication of the simulation to be viewed and analyzed in great detail. It also allows the simulation to be rewound, fast-forwarded, or paused. Detailed views allow the analyst to check and fully understand what is happening in the simulation. SIMLOX is also an effective way to present the simulation to an audience who just needs an overview of what the model represents. Although not used in the simulation itself, maps can be used to add a geographical representation to the game mode view. CATLOC is a powerful cost analysis tool that accommodates all the primary functions of LCC. Different uses may require different LCC models, so CATLOC allows analysts to utilize predefined templates, modify existing models or templates, or define their own cost breakdown. CATLOC provides a powerful user interface which allows the analyst to quickly understand the model being defined and to enter the data necessary to calculate the resulting costs. The strength of CATLOC is the analysis of the results. Not only can results be quickly and easily analyzed, but multiple models can be easily compared. The latest version of CATLOC also adds an extremely powerful sensitivity analysis capability. This demonstration will look at the main features starting with the model view. Part 2 will focus on the results viewer. As with the other tools in the OPUS Suite, the data to define the models is held in a series of tables. Sometimes the analyst will find it easier and faster to enter data directly to the tables, but the model view of CATLOC allows the analyst to quickly visualize the model and, more importantly, directly identify how different elements such as cost atoms and parameters are defined across dimensions and domains. Consider, for example, this cost model, where the model is being used to analyze some air systems operating across several air bases and over several years. The COF, or fuel operating cost atom, is used to calculate fuel usage over the life of the system. From the model view, it is clear that the COF is assigned to systems because they are what use the fuel. It is also assigned to the domain base in the dimension station. The domain base is a collection that only includes operating bases, so it makes sense that fuel is used by systems at operating bases. Finally, COF is also defined in time dimension. In this example, this assumes that different system types might use different amounts of fuel at different locations at different times. Expanding COF shows how it is derived, and selecting a different parameter, for example, NSYS, or number of systems, is defined by system type, by operating base, and time. The value grid can be easily adjusted according to the needs of the analyst. Data entry is another of CATLOC's strengths. High-level default values can be set and overridden by more refined data, or left as higher-level defaults. This is controlled by a clear hierarchy. Data can also be easily entered from external data sources or imported from other elements of the OPUS Suite. All data from the value view can be copied and pasted to or from external data sources such as Excel. Another feature of CATLOC is to be able to associate different costs with user-defined categories. In most cases, a complete model can be built using only the model view. The elements of the model view can be populated using drag and drop functionality. Importantly, all the data entered in the model view is held in the underlying tables, which can be easily edited should that be desired or necessary. Once the model has been built, clicking the Calculate or Sensitivity Analysis buttons will generate the results and activate the results view. Initially, the total costs are shown, but this is just the starting point. To redraw and analyze the cost model, the analyst simply drags dimension buttons to the appropriate axis. To find out more details about the results viewer and the sensitivity analysis capability, please continue watching Part 2 of the CATLOC introductory video. Using the cost model from our example in Part 1, we were able to easily see the total costs and adjust the charts by dragging dimension into the appropriate axis. We can start by looking at the LCC over time. Now we'll look at how these costs for each year are broken down. Clearly, COF is a cost driver, especially in years 2, 3, and 4. So let's focus on COF. Remember, COF was defined by system type, operating base, and over time. Let's begin by selecting only COS. Now let's look at how it is distributed by system or by base, or by base over time, or by system, base, and over time. Perhaps we are interested in how the fuel costs are split over the types of systems with bases as a proportion of the total cost. It is really just a case of dragging the dimensions onto the desired axis, and the chart is redrawn. Refining the results is also just a case of expanding the appropriate dimension tree. For example, let's go back to all level 2 costs. Simply select the top element of the cost tree and expand it as required. The chart is redrawn. We also included some categories in the input file. These can be toggled on and off in the result view, allowing the analyst to see which costs are included in the categories. Domains can also be used to filter entities included in the charts. For example, let's see which costs are associated with the entities included in the item domain. Results can be shown as pie charts or tabulated. All charts can be saved for later use. They can also be copied and pasted into external documents such as PowerPoint and Excel. User-defined reports may also be generated. These may include predefined reports useful for auditing the cost model and user-defined charts and tables. We'll now take a brief look at CATLOC's extensive sensitivity analysis capabilities. With CATLOC version 6 and above, sensitivity analysis can be carried out on a single or multiple parameter. The analyst can define several single or multi-sensitivity analyses. The analysis can be a simple increase or decrease of a parameter, or a more complex mix of variations for one or more parameters. Predefined or user-defined distributions can also be analyzed, and a simulation-type variation of the parameters may also be executed. In this example, a multi-parameter sensitivity was carried out, varying the parameters for each of the 1,000 replications according to the different distribution defined. The first thing to note are the markers indicating the cost changed as a result of the sensitivity. Note also that because this was based on the distribution, the means and standard deviations can also be shown. The results can also be viewed as a histogram, with results shown based on replications or density functions. Both can be accumulated. Multiple cases can also be included and directly compared. Let's include results from some other cases in sensitivity runs. This allows direct comparisons to be carried out, and also the risks and variations from the costs resulting from the parameters being varied to be assessed.